Hello, and welcome to the second video, where we talk a bit about the runtimes and some of the implications of these sorts we've done earlier. So basically, we're just filling out this table. This is a great table for you to have for reference. And hopefully it won't be too hard to figure out if you generally understand how a lot of these sorts work, which is what we were doing above. So let's just start with selection sort. Basically, what is the best and worst case runtime of selection sort? So keep in mind the way that selection sort works is you have a number of elements. You first scan through your array, find the minimum element, let's say it's this one, and then you swap with what is currently at the 0 index. You call that sorted, and then you do the same thing with the remainder of the array every time. So let's think about how this works out runtime-wise. So how long does it take to scan through an array, an unsorted array, looking for the minimum? Well, that's just going to be n, right? Because we don't know what order the elements are in, so if we just look through all of them, that's going to be n, right? Then we ask ourselves, how long do we have to do this? How many times do we have to do this? Well, we have to do this one time for every single iteration, right? We have to first figure out the 0 index, then the 1 index, and the 2 index, the 3 index, and the 4 index. So we have to do this n operation. We have to do it n times. So we're going to end up with an n squared runtime. You might say, well, do we have to do it? Does it actually take n time every time? Because notice in this example array, right, there are 6 things. So the first run of the loop, we're going to have to look for 6 things. Then once we sorted the first one, the next run of the loop, we're going to have to look through 5, then sort that one, then 4, 3, 2, 1. Well, remember what that is really that is a 6 plus 5 plus 4 plus 2 plus 2 plus 1, which is the same thing as 1 plus 2 plus 3, up to n, and this is equal to n squared, if you remember from some of our common series that we've seen in the past. So it's going to take n squared time to run selection sort. Now we can ask ourselves, does this differ in the best case or the worst case? And the answer is no, because regardless of what the elements are, you still have to look through the same number of them in order to find the minimum, and you still have to do the same number of swaps. So the best case and the worst case is going to be n squared, and it is not stable, as we did earlier. Right? That's selection sort. One thing to note here is you might ask, well, why would you ever use selection sort? These runtimes are terrible. One nice thing about selection sort is that it minimizes the number of swaps. We only swap an element when we strictly know exactly where it goes, as opposed to insertion sort, where we have a bunch of intermediary swaps or something. So if, for example, you have a system where it's very, very cheap to actually look through your array, look through your data, but it's very expensive to actually swap data, to actually write to your data, then selection sort might be something you would want to use. Anyways, that's a little out of scope of this question, so let's keep going. Insertion sort. How does insertion sort work? Well, insertion sort works in that it starts from the front, and then what we do is we always ask ourselves, okay, do I need to swap with the previous element? So if, for example, in this, let's say this element is bigger than this element, we would basically swap it up to here. And let's say we get to a point where we're looking at this element and it's bigger than all of these elements, we would swap it up to here, then to here, then to here, then to here, right? See that we have to swap one time for every place up we need to move. So if this is, 4 away from being where it needs to be, we need to make 4 swaps. And you can contrast that with selection sort, where we would have just figured out that we want to put, for example, this up, we want to move our thing into this index and we want to move this thing there and just use 1 swap. Okay. So the question is, how many swaps do we have to do in the best case and in the worst case for insertion sort? So let's look at the worst case first, because why not? So in the worst case, as is this example above, we have to do as many as n swaps for a given element, right? If this element is all the way back here and needs to be swapped up, we have to do something proportional to n, right? So n swaps per. How many times do we have to do that? Well, again, we have to do this once for every single node. So if every single node needs to be swapped up the maximum number of times it possibly can, meaning that every element we see is smaller than all the previous elements we saw, we're going to end up with n squared. Right? So our worst case is n squared. And an example of where that happens with insertion sort is going to be when your data is completely reversed. So if you have data that looks like this, 5, 4, 3, 2, 1, 5 we don't need to swap, but then going to 4, well, we're going to need to swap 4 with 5. Then going to 3, well, we're going to need to swap 3 with 4 and with 5. 2, 3, 4, 5, 1 is going to have to swap up with everything. So this is also a kind of, you see 1 plus 2 plus 3 plus 4, blah, 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 all the way up to n. So this is also going to be an n squared runtime. Okay, well, what's the best case runtime? Well, if the worst case runtime is created when it's the case that every element is less than every previously seen element, then the best case, quite logically, is going to be when every element that we see successively is greater than every element we saw in the past. So consider something like this: 1, 2, 3, 4, 5. 1 is trivially already going to be sorted, and then 2, we don't have to swap up, so we don't do anything. 3, we don't have to swap up, so we don't do anything. 4, don't swap up. 5, don't swap up. So we have to make no swaps, which means all we have to do is go through every element and just check once, is it greater than the previous element? And if the answer is yes every time, we're all good. So insertion sort has a best case of n, because that is the case where everything's already sorted. Okay, is it stable? The answer is yes, it is stable, because notice we only swap with an element when that element is strictly less than the element we're looking at currently. And so if you have two elements that are equal, you're not going to swap. And as I explained in the previous part, basically there's no way to jump over an element that is the same value as you, which is how you would make something unstable. Okay, great. Heap sort, heap sort, heap sort. Okay, so let's just think about heap sort a little bit. So heap sort is made by plucking off from a max heap every time. So the question is, first question is, there are two main parts of heap sort. We need to create the heap, and then we need to actually do the pulling every time. How long does it take to create a heap? Okay, well, in the best case, it takes n time to create a heap. This is when your heap has all the same elements, and you can just heapify it into an array immediately. And then in the worst case, it would take n log n to create a heap. And this is when you just have to do a lot of swaps when you're making your heap, right? Okay, that's to create a heap. And then how long does it take to pull an item from a heap? Well, in the best case, you just pluck the item off, and then you replace with the bottom right, and you don't have to do any swaps. Again, this might happen in the case where all the elements are equal inside the heap. You don't have to do any rearranging of the heap afterwards. And what is the worst case? Well, it's going to be log n, and that's where you do have to do a lot of syncing and swimming. Okay, so that is to pull one item. What is the time to pull n items? Well, if it takes constant time to pull an item, it would take n time to pull n items, and if it takes log n to pull an item, it would take n log n to pull an item, to pull multiple items. Okay, so basically, the lower bound on heap sort is going to correlate to the lower bound across both of these questions, right? Because if it took us n squared, for example, to create our heap, it wouldn't matter if we could pull it in n time, it would still be n squared. So basically, it's going to be the greater of the two best cases is going to be our final best case, and the greater of the two worst cases is going to be our worst case. We see they're the same here, though. So if we create a heap in n time, and then it only takes us n time to pull all those elements, we're going to end up with n total. And if it takes us n log n to create our heap, and it takes us n log n to pull every element, or if it takes us n to create our heap, and then it takes us n log n to pull every element, we're going to end up with a worst case of n log n. And as we saw in the example above, it's not going to be stable because this heapification process is not stable. When we do the heapification, we're not guaranteed to keep the relative ordering in place. And if we don't do it in the heapification step, it's not going to happen in the sorting step. Okay, that's basically how you do that. So merge sort. Okay, how long does merge sort take? So merge sort is interesting because we break our thing up. So let's say we start with an array like this. First thing we're going to do is we're going to break it up into halves. Then we're going to break it up into halves again, halves again, halves again, halves again, etc. And then we are going to combine those halves. And then we're going to combine those halves, right? So let's say that, for example, these boxes here represent things that are size 1. We're going to break all the way down, and then we're going to go all the way back up. Okay, so again, just like heap sort, there are two things to ask here. The first one is how long is basically how many recursive steps and how long per step. Right? What do I mean by that? So you see we have a bunch of recursive steps here with merge sort, right? We have to break up our array over and over again and then recombine it. So that's one thing. And then also at every step, we're going to have to do some work, right? We're going to have to recombine the elements together. Okay, so how many recursive steps? Hopefully you can tell that there are going to be log n of them. Why is it log n? Because we're splitting our array up in half every time, right? You could actually think of this as kind of 2 log n because we split our array up every time and then we recombine it together, but 2 log n is of course just log n. So that's how many steps there are. And then the question is, how long does it take to do each step? How long does it take to combine 2 arrays that are already sorted? And the answer to that is just going to be n. Here's a quick example of how that would work. Let's say you have 2 arrays that are already sorted, and it looks like this, right? Here's one array, here's another array. So imagine we're doing merge sort, and we're at the step where we're combining size 2 arrays into size 4, and these are our size 2 arrays. How long does it take to combine these into one sorted array? Well, it's actually really easy because all you have to do is you just start here and you start here. You start at the beginning of both arrays and you say, okay, which element is smaller? 0 is smaller, so that's the first element. Then because 0 is smaller, we move this arrow up here to the next thing, to 4, and then we say which is smaller, 0 or 1 or 4. It's 1, so we're going to put 1 next. We move this arrow up here. We say what is smaller, 2 or 4? It's 2. We do this. This arrow goes kind of off the edge, and we say what's smaller, 4 or nothing? 4. And then we move this arrow to the edge, and we're done. Right? So notice we were able to sort these 2 subarrays really quickly, and the reason we were able to sort them really quickly is because they were already sorted themselves, right? In other words, you may have been able to tell this was a linear process because all we had to do was just kind of scan across both arrays. So there is linear work being done per step in merge sort, and there are log n steps. In fact, really, the work done here in the first part is actually constant time because we're just breaking up the array. We're not actually doing anything. And then the work done from here on is actually linear. Either way, we're doing a linear process n times. So we're going to end up with an n log n runtime, right? And again, it's going to be stable, as we talked about above. And that's because each individual subsort is stable. So then the full thing is going to be stable as well. Okay, why are the best case and the worst case both n log n? And it's because there's no difference, right? Regardless of what the elements are, we're still going to break them all up into halves every time. We're still going to recombine them in the same number of steps. Okay, quicksort. Quicksort is a little bit different. Quicksort's a little trickier. So the first thing I noticed about quicksort is that the best case and worst case are probably going to differ. Why is that? Because I see that depending on what pivot we use, right, the number of things we're going to sort per step is going to be different, right? Notice this first time we did quicksort. In this first iteration, we used 2 as our pivot, and we ended up sorting things into here and into here, right? And then on later steps, you might end up getting a pivot that sorts the data better, right? Whenever the actual data that you're processing, whenever the actual numbers involved affect how you sort things, that's a pretty good indicator that you're going to have differing best case and worst case here. Okay, so what is the best case for quicksort? Well, the best case for quicksort is going to happen when we split up our data relatively evenly every time, right? Because remember, quicksort is fundamentally a recursive algorithm. We're going to start with a whole list, a whole array, and then we're going to sort one thing in the middle, and then we're going to have 2 subarrays of unsorted elements. Then we're going to split one thing, sort one thing in the middle, and have 2 subarrays again of sorted and unsorted elements like that, basically. Okay, so if our pivot for quicksort is good, meaning that it divides our data equally every single time, that means we're going to split the data in half every time. Splitting things in half every time is a really good indication that something's going to be a logarithmic runtime. Okay, so in other words, just like how merge sort had a kind of tree height of log n, we had to do log n recursive steps. In the best case, quicksort is going to do log n recursive steps because we're going to break things up evenly. And then we ask, well, how long does it take to actually do each step, right? We say, how many steps? In the best case is going to be log n. And then how long per step? Well, if we look up here again, remember all we did is we chose a pivot and then we just scanned left to right and we said, okay, this one's smaller, it goes here, this one bigger, it goes here, smaller, bigger, et cetera, et cetera. Okay, well, that sounds pretty linear to me. So that is just going to be a linear time. So that is going to give us n log n as our best case, right? Meaning that when we split up the data relatively evenly, it's going to work very similarly to merge sort, how we're splitting things in half every time and we're doing a linear process on every one of the steps. Okay, but what's the worst case? Well, the worst case is pretty similar actually to what we got up here, right? Because if the best case is we're going to split up data evenly every time, worst case is we're going to split it up not very evenly every time. And we see that here in this case where, notice, we got a lot of steps here where we ended up only being able to sort, say, one element at a time, right? Like this first step is not very good, right? The split is not very good. So that's going to be our worst case. Our worst case is when we're only able to sort one element every time. And that's basically when our pivot's really bad. So let me give you an example. Let's say we have the data 1, 2, 3, 4. We choose 1 as our pivot. So then we're going to split into 2 arrays, everything that's less than 1 and everything that's greater than 1. Okay, well, that didn't do a lot. Then we split it into 2 arrays, starting with 2, because that's our next left pivot. Everything that's less than 2, everything that's greater. Not a lot. Same thing. We now are going to look at 3. We look at everything that's less than 3, everything that's greater than 3, then we look at 4, it's trivially sorted, right? So that's going to be our worst case for quicksort, is when our pivot makes it such that we only sort one element per time, right? This can happen if the array is already sorted. It can also do the same thing if the array is backwards, because if the array is 4, 3, 2, 1, whoops. If the array is 4, 3, 2, 1, we're going to have the same problem where we're only sorting one element at a time. It's just instead of everything going to the right of that pivot, it's all going to go to the left of the pivot every time, right? Because we select 4 as our pivot, 3, 2, and 1 are all going to go to its left. Okay, well, so if we're doing an end process and we are, if we're doing a process that still takes time n, and we're only sorting one element every time, how many steps does that mean? It means that we'd have to do it n times, and this n process n times, so we'd end up with n squared. Great, and then quicksort is also stable if we make sure to make it the case that something to the left in our recursive step stays to the left and something to the right stays to the right, right? As long as we ensure that, as long as we should ensure stability every step, the whole thing will be stable. But in the generic case, it isn't necessarily. Yeah, this is one of the reasons people oftentimes like to use merge sort over quicksort, is because merge sort is always stable. Quicksort is stable depending on the implementation. So I'm going to say yes/no, even though the actual worksheet says yes. It depends. Okay, these are all of the comparison-based sorts. And then these ones here are counting sorts. So we didn't really talk about these earlier in the worksheet. I'm just going to give you a quick rundown of them and the runtimes associated with them. So counting sort is a non-comparison based sort. Basically what we do is we have what we would call an alphabet. So it's a number of possible values we could have, and then we keep track of that number and we sort based off that. So let me give you an example. Let's say we have an array like this. Let's say it looks like this. Oops, it's supposed to be a 2. And let's say that we know that the array is only ever going to contain the numbers 0, 1, and 2. Therefore, our alphabet is going to be only 3 different characters, right? There are 3 possible characters. So what we do is we create a new array with a size equal to the size of our alphabet, right? This represents 0, this represents 1, this represents 2. And then what we're going to do is we're going to start these all at 0, and we're just going to scan left to right through this array and count up the number of things we see. So we see a 2, we see a 1, we see 0, 0, 0. I probably don't have to tell you how to do this. We're going to end up figuring out that we have 2 zeros, we have 2 1s, and we have 3 2s, right, in this total array. Now, we don't need this original array anymore. We can just take this and build a new array based off of it. So all we have to do is say, okay, we know 0 is the minimum element of our alphabet, and we know we need 2 of them. We know we need 2 1s, and we know we need 3 2s. We can do this, right? So this is how we end up with our array, right? We don't rearrange the original array. Rather, we kind of take everything we need from the original array, take all of our information, and we create a new array with it. Notice also that there are no comparisons here, right? We never did a swap or anything. We just counted up the number of possible things, added them together, and did this. Okay, so this is a counting sort. Notice there's some specific criteria, though, that have to be met to do a counting sort. First of all, you have to have a clearly defined alphabet. So if you're sorting a set of data and you know exactly what the data is going to be, that works well. But if you just want to sort, numbers from 1 to 10,000, well, then your alphabet needs to be size 10,000, which isn't going to be particularly efficient, right? So you have to have a very clearly defined alphabet. But if you can, you end up with a linear runtime, or more specifically, the way we would describe it in this class is n plus r, where n is the number of elements in the original array, because remember we had to scan over this, and then r is the radix of the alphabet, meaning how many different elements there are in the alphabet. In this case, the radix is 3, so r would be equal to 3, right? And we know that because we have to similarly kind of add up and scan over this array later. Okay, and that runtime does not differ based off the data. It differs based off the alphabet, but not off the data. And this is also going to be stable because really you don't even need a notion of stability here, right? All the elements are clearly defined. There's no way to have a 4A, 4B type thing like we had before. So we'll just say it's stable. Okay, so the big drawback with counting sort is, of course, that you need to have this really clearly defined alphabet. And if the alphabet gets really big, like you're trying to sort words or huge amounts of numbers, it doesn't work very well. So the idea of LSD and MSD radix sort is to kind of subdivide sorts into these alphabets and sort them that way. So LSD sort is going to be pretty straightforward, I think. If you have a bunch of numbers, let's say you have something like this. You have something like this. All you're going to do is you're going to sort them by the you're going to sort them by the last element first, and then the second to last, and the third to last. What do I mean by that? So first we look at the last number of all of them, and we're going to do a counting sort on this. Remember how in counting sort, all we did was we looked at the number of zeros, the number of ones, the number of twos. Well, now our radix is just 10, right? Because there can be 10 different things that any given space can be. And we're going to sort it similarly. So we're going to go left to right and say, okay, we sort all the things that are 0 first, like that. Then we sort all the things that are 2, and there were no ones, right? So we sorted only based off the last digit. And if there are ties, we just go left to right in terms of the order they originally appeared in the array. Okay, then we sort the second to last. Right, so we say, okay, we have things that have 1, so those are going to be the minimum, then something that has a 5, then something that has a 6, just like this. And then we sort the third to last, which in this case is going to be the most significant digit. Well, 1 is the smallest, then 2 is the smallest, then 3, and then 4. And so we end up fully sorted like this. Okay, so why does this work? This works because, spoiler, this is stable. Basically, when you sort something by the ones place, and then you sort it by the tens place stably, that's equivalent to sorting it by both the ones and the tens place. So what you'll notice is that this iteration here, before we sort by the hundreds place, everything is actually sorted by the tens place, right? 12, 12, 50, 60, right? And that generalizes to any set of data. So the connection here is a little bit hard to see without code, but hopefully you can see. We just said radix sort. It would be too hard to say, okay, we have an array of 1 to 1,000, put everything in this array, and then sort based off that. That would take a lot of memory. So instead, what we're doing is we are creating a radix of 10. We're sorting everything by the ones place, then the tens place, and the hundreds place. And we are counting on the stability of LSD sort to note that once we sort by the ones and tens place, they will remain sorted by the ones and tens place, then ones and tens and hundreds, et cetera, et cetera. Okay, that's a lot of explanation on this. So let's just get to the runtime. I'll basically just give it to you and kind of explain it. We normally say it is L times n plus r. So we would still describe this as a linear runtime. But what does all of this mean? So n plus r, just as before, n plus r is going to be the number of elements we have plus the radix, right? That's how long it's going to take to do every kind of individual subsort here. And then how many total sorts do we have to do? How many runs of this algorithm do we have to do? Well, the number of runs is going to be linearly proportional to the amount of data we have to sort. In other words, there are 3 things we need to sort on in this data. So it's going to take us 3 runs of the algorithm. So that's L. L represents the length of the word or the number in this case. Okay, MSD is going to be a very, very similar process, except instead of sorting from least to greatest, we're going to sort from greatest to least. So let's take this same set of data here. Let's take this same set of data and do an MSD sort on it. So now let's sort by the most significant digit. So what we're going to do is we're going to say, okay, here are the ones, here are the twos, here are the threes, here are the fours. Okay, and another thing we're going to do is we're going to put them all in separate boxes. And then we're going to sort these boxes individually. So all these boxes have one thing in them, but if they had 2 or 3 things in them, we would then sort those 2 and 3 things as a subset. Okay, why do we do that? Well, because right now we can actually short circuit right here. Notice that every hundredths place, every most significant digit in this set of data is actually different, which means that once you sort it by the most significant digit, it's actually done, right? There's no need to now subsort by least significant digit. Okay, so basically you end up with a better runtime here. So what is the best case runtime? Well, if the best case runtime of LSD was basically the time to do a counting sort times the number of times we had to do the counting sort, notice here in this particular best case, we ended up with a single run of the algorithm. So we end up with an n plus r runtime in the best case. And in the worst case, we're going to have the same thing that we had with our regular LSD, because we're going to have to sort as many as L times, right? If the data is all the same. Okay, great. This worksheet says that MSD is stable. This also depends. Oftentimes we consider it not stable depending on the implementation. So if the worksheet says yes, go with yes, but it is possible for it to not be. Okay. That is basically an explanation of all these sorts, how they work generally speaking, and why they have the runtimes they do. And I hope this was helpful.